stars. You look up, and they all seem the same. Little white dots scattered across the dark, but that sameness is an illusion, a trick of distance. Stars are not one thing. They come in a staggering range of types, and the differences between them are almost impossible to believe. Some are so small and cool they can barely be called stars at all, burning so slowly they will outlive the universe as we know it. Others are so massive they tear themselves apart in explosions that briefly outshine entire galaxies. Some are corpses, dead stars that keep spinning hundreds of times a second. And one of them, the one you know best, is not even the color you think it is. Today, we're going through every type of star, from the smallest, dimmest embers to the monsters that end in catastrophe. By the end, you will never look at the night sky the same way again. Let's start at the bottom with the most common star in the universe, the one you have almost certainly never seen: red dwarfs. Let's start small, really small. A red dwarf is the runt of the stellar family, and yet it is by far the most common type of star in existence. Roughly 3 out of every 4 stars in the entire universe are red dwarfs. They are everywhere. And here's the first strange fact. Despite being the most numerous stars of all, you cannot see a single one of them with your naked eye. Not one. They are simply too dim. A red dwarf has only a fraction of the mass of our sun, sometimes as little as 1/10. And with less mass comes less pressure in the core, which means fusion happens slowly, grudgingly, at a fraction of the rate inside a normal star. The result is a cool, faint, deep red glow, barely a whisper of light compared to the sun. But here is what makes them extraordinary. Because they burn their fuel so slowly and so efficiently, a red dwarf can keep shining for an unimaginably long time. Our sun will last about 10 billion years. A small red dwarf can last for trillions of years. That is far longer than the current age of the universe, which is only about 14 billion years old. Let that sink in. Every red dwarf that has ever formed is still shining today. Not a single one has ever died of old age because the universe simply has not existed long enough. They are the marathon runners of the cosmos, the stars that will still be glowing long after every other kind has gone dark. There is another reason red dwarfs matter enormously. Because they are so common and live so long, they are the galaxy's best hope for hosting life. Most of the potentially Earth-like planets we have discovered orbit red dwarfs, simply because there are so many of these stars to search around. Our nearest neighbor star, Proxima Centauri, just over 4 light years away, is a red dwarf, and it has at least one planet in its habitable zone. But there is a catch. Red dwarfs are often violent in youth, blasting out enormous flares that could strip the atmosphere from a nearby world. So they offer a strange bargain, almost eternal warmth, but a stormy, dangerous start. Whether life could survive that trade off is one of the biggest open questions in the search for life beyond Earth. But if red dwarfs are the smallest true stars, what about the objects that tried to be stars and failed? Brown dwarfs. Here is where the definition of a star starts to break down. A brown dwarf is a failed star, an object that formed just like a star, collapsing out of a cloud of gas, but never gathered enough mass to ignite properly. To become a true star, an object needs enough gravity to crush its core hot enough to fuse hydrogen, the most basic nuclear reaction that powers stars. A brown dwarf falls just short. It sits in a strange middle ground, heavier than a giant planet like Jupiter, but lighter than the smallest real star. Too big to be a planet, too small to be a sun, and so it glows faintly, not from hydrogen fusion, but from the leftover heat of its own formation, slowly cooling over billions of years like a dying ember pulled from a fire. Some brown dwarfs are so cool you could, in theory, touch their surface without being instantly vaporized. There are brown dwarfs out there with temperatures close to that of a cup of hot coffee. Think about that. An object the size of a small star, drifting alone in space, no warmer than something you could hold in your hands. They are the in-between things, the almost stars, the cosmos hedging its bets. And they are frustratingly hard to find. Because they emit almost no visible light, glowing mostly in infrared, brown dwarfs stayed entirely hypothetical for decades. Astronomers predicted they should exist long before anyone actually confirmed one. It was not until the mid negative 1990s that the first true brown dwarf was definitively identified. Since then, we have found that they may be nearly as common as stars themselves, a vast hidden population drifting invisibly through the galaxy. Some even have their own weather, with clouds of hot mineral dust and molten iron rain falling through their skies. A world where it rains liquid metal on an object that is neither quite a star nor quite a planet. But let's move up now to the star we know better than any other. Yellow dwarfs. This is home. Our sun is a yellow dwarf, and it's the star every other one gets measured against. But right away, there's a problem, because the name is a lie. Our sun is not yellow. It's white, pure white. If you could see it from space, floating against the black, it would be a brilliant white disk. The only reason it looks yellow or orange or red from the ground is that our atmosphere scatters away the blue light, tinting what reaches your eyes. Out in space, its true color is white. A yellow dwarf like the sun is a middle class star. Not tiny like a red dwarf, not a giant. It sits in the comfortable middle, fusing hydrogen into helium in its core steadily and reliably for about 10 billion years. Our sun is currently about halfway through that life. It is, in a sense, in its prime. It's worth pausing on just how ordinary and yet how vital our star is. The sun converts about 4 million tons of its own mass into pure energy every single second, and it has been doing so for 4.5 billion years. That energy takes a leisurely journey too. A photon born in the sun's core can take tens of thousands of years just to bounce its way out to the surface, and then only 8 minutes to cross the 93 million miles to your eyes. So, the sunlight warming your face right now began its life in nuclear fire longer ago than human civilization has existed. Every yellow dwarf tells the same steady story, a long, stable middle age, powering whatever worlds happen to orbit it. But this stability is temporary. Every yellow dwarf is living on borrowed time, slowly burning through the hydrogen that keeps it stable. And when that fuel begins to run out, the star does not simply fade away quietly. It does something dramatic. It begins to swell, which brings us to what our sun will one day become: red giants. When a star like our sun runs low on hydrogen fuel in its core, everything changes. The core, no longer able to push back against gravity with the same force, begins to contract and heat up. And this triggers something counterintuitive. The outer layers of the star begin to expand, ballooning outward to enormous size. The star becomes a red giant, and the scale of this is difficult to grasp. When our own sun becomes a red giant, in about 5 billion years, it will swell so large that it may swallow Mercury, then Venus, and possibly reach all the way to Earth's orbit. The planet you are standing on right now may one day be swallowed whole by the very star that gives it life. The surface of a red giant is actually cooler than a normal star, which is why it glows red rather than white. But it is vastly larger, and so, despite being cooler, it shines far brighter overall simply because of its enormous surface area. Red giants are the retirement phase of medium stars, a brief, bloated, dramatic old age before the end. To picture the sheer size, consider a famous red giant you can actually see. Aldebaran, the orange eye of the constellation Taurus, is a red giant roughly 40 times the diameter of our sun. And that is a modest example. If some of the largest known red giants were placed where our sun sits, their surface would extend past the orbit of Mars. These stars are so distended that their outer layers are barely held on at all, and they constantly shed material into space, wrapping themselves in expanding shells of gas. Watching a red giant is, in a sense, watching a star slowly turn itself inside out. And that end, for a star like the sun, is surprisingly gentle. But before we get there, we need to look at the giants that make our sun look like nothing at all: blue giants and supergiants. Now we scale up in a way that defies imagination. The most massive stars in the universe are the blue giants and blue supergiants. Where our sun is a modest yellow dwarf, these are monsters, tens of times the mass of the sun, and tens of thousands of times more luminous. They burn blue-white, the color of the hottest flames, because their surfaces are ferociously hot. And here is the cruel trade-off of being a giant. The more massive a star is, the faster it burns through its fuel. It seems backwards. A blue supergiant has vastly more fuel than the sun, yet it burns through all of it in just a few million years, a cosmic blink, while a tiny red dwarf sips its fuel for trillions. Live fast, die young. These giant stars are so luminous that we can see them across enormous distances. Many of the brightest stars in the night sky, the ones that actually catch your eye, are these rare, brilliant giants, not the humble red dwarfs that vastly outnumber them. They are the celebrities of the galaxy, blazing and short lived. Take Rigel, the brilliant blue white foot of the constellation Orion. It shines with the light of tens of thousands of suns and sits over 800 light years away, yet it is still one of the brightest stars in our sky. That is how staggeringly luminous these giants are, and their rarity is extreme. For every blue supergiant in the galaxy, there are many millions of red dwarfs. When you pick out the brightest, most eye catching stars on a clear night, you are almost always looking at these rare giants burning through their brief, spectacular lives, not the countless dim stars that actually make up most of the universe. And when a star this massive finally exhausts its fuel, it does not swell gently and fade. It detonates, which brings us to the most violent event stars are capable of. Supernovae. This is how the giants die. When a massive star runs out of fuel, the fight it has been waging for millions of years, gravity pulling in, fusion pushing out, ends in an instant. Fusion stops. Gravity wins completely. The core collapses in less than a second, and the outer layers come crashing down, then rebound in a shock wave of unimaginable force. The star explodes. This is a supernova, and it is one of the most powerful events in the entire universe. For a few weeks, a single exploding star can shine as brightly as an entire galaxy of 100 billion stars combined. A single dying star, briefly outshining 100 billion others. And here is the part that connects directly to you. The explosion is so violent, so hot, that it forges heavy elements that could never form inside a normal star. Gold, silver, iron, the calcium in your bones, the iron in your blood. All of it was cooked inside massive stars and scattered across space by supernovae billions of years ago. You are quite literally made of the ashes of dead stars. Every atom heavier than iron in your body was forged in a stellar explosion. There is a particular kind of these explosions worth knowing about. When two dead stars, two white dwarfs, spiral together and one tips over a critical mass limit, it detonates in a remarkably consistent way, always with nearly the same brightness. Astronomers realized they could use these as cosmic measuring sticks, standard candles, to gauge distances across the universe. It was precisely these exploding stars that revealed one of the most shocking discoveries in science, that the expansion of the universe is not slowing down as expected, but speeding up, driven by a mysterious force we now call dark energy. So dying stars did not just build your body. They revealed the ultimate fate of the cosmos itself. But a supernova is not the end of the story. It leaves something behind, and what it leaves depends on how massive the original star was. Neutron stars. When a massive star explodes as a supernova, the core does not always vanish. Sometimes it survives, crushed into something almost impossible to describe. A neutron star. Imagine taking a star more massive than our sun and compressing it down into a sphere only about 20 kilometers across, the size of a city. That is a neutron star. The matter inside is so dense that a single teaspoon of it would weigh billions of tons here on Earth. A single sugar cube sized piece of a neutron star outweighs a mountain. The gravity is so intense that if you dropped an object from just 1 meter above its surface, it would hit the ground at a significant fraction of the speed of light. And they spin. Because the collapsing core conserves its rotation, neutron stars spin at astonishing speeds, some rotating hundreds of times every single second. Some of these spinning neutron stars beam out radiation from their poles like a lighthouse, sweeping across space. When that beam sweeps past Earth, we detect it as a precise, rhythmic pulse. We call those pulsars, and they are so regular they rival atomic clocks. A city-sized corpse of a dead star, spinning hundreds of times a second, keeping better time than almost anything humans have ever built. And when two neutron stars collide, something spectacular happens. The crash sends ripples through the fabric of space time itself, gravitational waves that we can now detect on Earth, and it forges a burst of heavy elements in an instant. In fact, much of the gold and platinum in the universe, the metal in a wedding ring, may have been created in the collision of two dead stars billions of years ago. The most precious things we own were made in the wreck of stellar corpses. But neutron stars are not the densest thing a dying star can leave behind. For the very largest stars, the collapse does not stop at all. Black holes, for the most massive stars of all, the supernova leaves behind something even more extreme than a neutron star. When the core is heavy enough, nothing can halt the collapse. Not the pressure of neutrons, not any force known to physics. The core crushes itself past every limit, collapsing into a single point of infinite density, and around it forms a region where gravity is so strong that not even light can escape. A black hole, this is the final fate of the giants, the ultimate end state of stellar death. Where a neutron star is a corpse you could theoretically still see, a black hole is a corpse that has removed itself from the visible universe entirely, wrapped in a boundary of no return. It is the strange truth of stars that the biggest, brightest, most brilliant of them end not as glowing embers, but as invisible pits in space, silent and dark. The more spectacular a star's life, the more extreme its death. But not every star dies in fire. Let's go back to the quieter ending, the one that waits for stars like our sun. White dwarfs. Most stars, including our sun, are not massive enough to explode. So, what happens to them? After a medium star swells into a red giant and puffs away its outer layers into space, forming a beautiful glowing shell of gas, all that remains is the exposed core, a white dwarf. It is roughly the size of the Earth, but it contains as much mass as an entire star, making it incredibly dense, though nowhere near as extreme as a neutron star. A white dwarf produces no new energy. Fusion has stopped completely. It simply glows from leftover heat, radiating away the warmth of its former life, cooling over billions upon billions of years. And here's the quietly haunting part. A white dwarf takes so long to cool completely that no white dwarf in the universe has ever fully faded to black. The universe is not old enough. The theoretical final state, a cold, dark, crystallized ember called a black dwarf, does not yet exist anywhere. Not a single one. They are a type of star that the cosmos has not had time to create. This is the peaceful death, the slow fade, the fate that waits for the sun in the distant future. But there is one more kind of star, and it may be the strangest of all, because we are not even sure it counts as a star. Variable and exotic stars. Beyond the main types, the universe hides a whole zoo of stranger stellar objects. There are variable stars, whose brightness pulses up and down in a steady rhythm as they physically swell and shrink, breathing like a living thing. These pulsing stars turned out to be one of the most important tools in all of astronomy because their rhythm reveals their true brightness, letting astronomers measure the distance to faraway galaxies and ultimately discover that the universe itself is expanding. There are binary stars, pairs locked in orbit around each other, which is actually more common than a lone star like our sun. When you wish upon a star, you are often wishing on two. And there are truly exotic possibilities at the edge of physics, hypothetical stars powered by dark matter, or the theoretical quark star, even denser than a neutron star but not quite a black hole, sitting in a gap we are not sure nature ever fills. These are the outliers, the special cases, the reminder that even our neat categories are just the beginning of the cosmos's imagination. The takeaway. So look up again. Those little white dots are not the same at all. There are red dwarfs, tiny and dim and nearly eternal, outnumbering everything yet invisible to your eyes. There are brown dwarfs, the failed stars caught between planet and sun. There are yellow dwarfs like our own, white despite their name, living steady middle class lives. There are red giants, the bloated old age that will one day swallow the earth. There are blue supergiants, the brilliant short lived monsters that live fast and die young. There are supernovae, the explosions that forge the atoms in your blood. There are neutron stars, city-sized corpses spinning hundreds of times a second. There are black holes, the invisible graves of the greatest stars. There are white dwarfs, the slow fading embers no older than the universe can allow. And there are the exotic ones, the pulsing and the paired and the purely theoretical, sorted by mass, by color, by temperature, by how they will die. Every one of them a stage in a single grand story, the birth, the life, and the death of stars. And every heavy atom that makes up you, your bones, your blood, the screen you are looking at was forged inside one of them and scattered across space so that billions of years later it could look back up and wonder. Not bad for stick figures on a rock.